Good morning, everyone. Welcome to our NMIS Insights webinar on Rotary Friction Revolution. If you don't mind bearing with us just for a moment to give our attendees time to connect. Thanks very much. Thank you. Thanks for those that have just joined us. If you don't just bear with us for one moment, just to allow people time to connect, and then we'll get started. Thank you. Okay, good morning, everyone. Welcome to this week's NMIS Insights webinar on Rotary Friction Revolution. And thanks very much for your patience. And we'll now get the session started, and I'll hand you over to my colleague Stuart Laidlaw. Thank you.
Good morning, everyone. Welcome to our latest in the NMIS Insights online webinars, where today we will discuss the fascinating subject of rotary friction welding. Today we will be joined by Richard March from Rolls-Royce, then colleagues Laurie De Silva and Ioannis Violatis from the NMIS Specialist Centre, the Advanced Forming Research Centre. My name is Stuart Laidlaw. I'll be your host this morning. I work for NMIS and I support the business development requirements of AFRC. So before we get underway, there's just a few points of online housekeeping to observe. And just to let you know that the webinar is being recorded and will be made available on our YouTube channel. Your microphones and webcams will be turned off just to avoid background noise. And there will be time, particularly at the end, there will be time for questions. So if you want to type in your questions via the chat tool during the presentations, then I'll be sure to ask them to the panelists at the end. And lastly, please take time to complete our survey that will be sent after the webinar. So just a very brief introduction from me regarding the NMIS, National Manufacturing Institute Scotland. So we're a group of industry-led manufacturing research and development facilities where research and industry and the public sector work together. Our goals are to increase productivity, stimulate investment and increase manufacturing competitiveness, catalyse job creation and strengthen supply chains. Importantly, inspire and attract talent to equip the current and future workforces with the skills they need. And of course, work with manufacturing businesses of all sizes and multiple sectors, providing benefits across the whole of Scotland. We're part of the One Scotland team, which is operated by the University of Strathclyde and supported by a number of government and external stakeholders such as Scottish Government, the High Value Manufacturing Catapult and Scottish Enterprise. The NMIS group is made up of a number of different specialist centres. The Advanced Forming Research Centre, where Laurie and Ioannis work, is one of the key open centres now, and the Advanced Forming Research Centre has been in operation for over 10 years. We also have the Lightweight Manufacturing Centre in operation, which has been running for 3 years. And then we have in our development, Digital Factory Collaboration Hub and the Manufacturing Skills Academy. So after that brief introduction to NMIS, I would like to introduce to you Richard March. I'm delighted that Richard has joined us today and will provide a short introduction to this subject from the perspective of Rolls-Royce. Just as a brief background, Richard joined Rolls-Royce in 1985 after gaining a physics degree from the University of Birmingham, and he's currently leading the welding and joining team for Rolls-Royce with responsibilities in aerospace, nuclear and energy sectors. Richard is a chartered engineer with the Royal Aeronautics Society. So without further ado, I would like to hand over to Richard.
Thank you, Stuart, and good morning, everyone. Next slide, please. So today's webinar is about some opportunities presented by inertial welding, and this is a technology that's been used within Rolls-Royce for around about 50 years. However, it's fair to say that we've only really started using it seriously over the past 20 years, and this started with the purchase of an MTI 2000B inertial welding machine. We now have two of these 2000B machines. We've got one in the UK and one based in Germany. And these are used to join critical rotating parts in gas turbine engines. And you can see, looking at the top right picture on this slide, that really shows the core of the gas turbine. And the parts we use inertial welding to join are typically the compressor drums, turbine disks, as well as the shafts that run through the centre of the engine. And I think probably pretty obviously, it's absolutely essential that these joints are the highest quality. A little bit about the 2000B machine. These machines are capable of providing very high process loads. The 2000 in the machine's name actually represents a 2,000 ton end load. So when you're making the inertial weld, the two parts can be pushed together with a load of up to 2,000 tons. And this is really illustrated by the picture in the bottom right of the slide. And what you can see here is a 350mm diameter test weld being made. So this is a solid steel bar, and one side is clamped in position, and the other side is spun at high speed. And you can actually see a little bit of one of the flywheels. So the rotating side spins at high speed with some very heavy flywheels attached to it. So you've got an awful lot of rotational energy stored. The parts are pushed together, and then the frictional heating softens the and essentially forges the two halves of the joint together, giving you a very high quality bond. And in fact, when making one of these 350mm bar welds, which are generally used to test the machine, you can actually feel the heat coming off it from some way away. So there's clearly a lot of energy stored in this process. Next slide, please, Stuart. Inertial welding has many benefits, Royce. As I mentioned, the process is a solid state process, and it is capable of giving very high joint quality. So you can actually get joint properties that are comparable with parent material. And for things like critical rotating parts, this is absolutely essential. The other main reason is using it to join alloys that can't generally be welded by conventional fusion welding processes. Within a gas turbine, there are a lot of fairly complex alloys, and we put an awful lot of time and money and effort into designing these very exotic alloys that have got very precise properties. If you then go and fusion weld them, essentially you're melting it all into a liquid pool, and it can solidify in all sorts of different ways. So you generally don't get those properties that you put so much time and effort into trying to achieve. With inertial welding, being a solid state process, you retain a lot more of the properties. So it's got a lot of benefits. Just to talk about a couple of the other benefits, it's an automated process. So you don't need qualified welders. It's a self-cleaning process. The fact that actually you are flushing the interface material out as you push the two halves together means that you flush out any contamination at the interface. And it's good for joining dissimilar materials. The picture on the bottom right is a turbine disk. And in this case, we want different properties from different parts of the disk. So what we do is we inertial weld two different nickel alloys in order to achieve this. And it's very reliable. I mean, the right first time values are generally well over 99% because of that automated repeatable nature. Next slide, please, Stuart. So a little bit about the AFRC. Worked closely with the AFRC for a number of years now, and this has been vital for both developing the inertial welding. And in addition to the really quite significant technical expertise within the AFRC, they have 2 industrial scale machines, and this is really important, because what it does is it allows us to do industrial scale trials without disrupting one of our 2 production machines, which is key, really. A further benefit is that these machines at the AFRC, which were also applied by MTI, are much more highly instrumented and much more flexible than our production machines. I mean, the production machine will be designed for a particular purpose. With the research and development machines, you've got that much greater flexibility, and we can get a lot more out of any trial that we run. And as I say, the AFRC is key for this and key for development. So last slide, please, Stuart. So there's a little bit of a lag, but this last slide is really just talking about benefits for the nuclear industry. Within Rolls-Royce, all our experience is really within gas turbines. However, there are a number of clear benefits that I believe inertial welding can offer the nuclear industry. And I know that Laurie and Johannes are going to talk about this in a bit more detail later in the presentation. But a couple just to mention really are, particularly when you're welding stainless steel, there's quite a big issue really with ultrasonic inspection. You can find a grain structure that does make ultrasonic inspection really quite difficult. Inertial welding is much better in that respect. You've got a grain structure that is much more favourable for ultrasonic inspection. And in addition, you don't tend to get the same level of sensitization of stainless steel that you would with a fusion welding process. And also, in addition to this, we've got the other benefits, the self-cleaning process, the automation, and so on. So I think that there are potentially a number of good benefits. I think that inertial welding can benefit the nuclear industry. So with that, I'll hand over to Laurie.
Okay, well, thank you very much, Richard. Just before we hand over to Laurie, I'd just like to say that just remind everybody that if they've got any questions for Richard on his presentation, his introduction, then please type them into the chat, and we'll get the chance to put them to Richard at the end of the session. Now I'd just like to introduce my colleagues from the AFRC, who are going to present some work that, although they haven't, Rolls-Royce hasn't been involved in this work that Laurie and Johannes are going to present. It's certainly something where the Rolls-Royce are a key partner in the AFRC friction welding programme, and are highly involved in everything that we're doing. So I'd like to introduce to you my colleagues, Dr. Laurie De Silva and Dr. Johannes Violatis from the AFRC's Materials Characterisation and Residual Stress team. Laurie leads our welding and joining theme and has been at the AFRC since 2014, focusing on rotary friction welding for the last 3 years. Johannes leads our materials modelling theme and has been with the AFRC since 2015, working primarily on modelling of manufacturing processes, microstructure, evolution and mechanical properties definitions, and also residual stress generation and evolution in a range of metallic materials. So without further ado, I will hand over to Laurie.
Good morning, everyone. Just trying to find my screen to share with you. Okay, hoping everyone can see the slides.
That's perfect.
Okay, well, good morning, everyone. Today I'll be discussing the feasibility of rotary friction welding in nuclear applications, along with my colleague, Dr. Ioannis Vailatos. I'll give you an overview of what we'll discuss today. So I'll give you an introduction into bimetallic welds in the nuclear sector, some of the advantages of rotary friction welding over fusion welding. I know Richard's gone over some of them, but just to reinforce the issue. And I'll discuss some of the AFRC's rotary friction welding capabilities. We'll focus on a case study for reactor pressure vessel nozzles and pressurized water reactors. We'll discuss some of our solid state welding trials, some of our post-weld analysis, residual stress capabilities, some of our residual stress analysis from the work we've done, our modeling theory, and some conclusions. So an introduction to bimetallic welds in the nuclear sector. Biometallic welds play a critical and indispensable role in the primary heat transport piping system of nuclear reactors. So you normally have a heavy section, low alloy steel component that's connected to a stainless steel primary piping system. And I've given an example schematic of one from a paper by Wang et al. In the Journal of Engineering Failure Analysis in 2013, just there. So the Austenitic stainless steel tubes illustrated in the green are used in high temperature sections where we need increased creep strength and a resistance to oxidation. Whereas in the primary boilers and the pressure vessels where the temperatures are lower, you can normally get away with using a more economical low alloy ferritic steel. So therefore the bimetallic joint can provide the best of both worlds in terms of properties for the application. In terms of the current manufacturing route for these bimetallic joints, if you look at the very simple schematic at the bottom, we have ferritic steel, and you can have up to 1 or 3 layers of a thin buttering material applied to the end of the vessel nozzle. Those layers are normally about 5 to 8 millimeters in thickness, and the first layer is often over-alloyed with respect to chromium and nickel, and that's to compensate for any dilution from diffusion through to the base material. There's also a filler material usually required, and then after all the buttering and filler material, which are normally added via submerged arc welding, there's often residual stresses generated within the joint, so a post-weld heat treatment is often required. A kind of summary of the key issues that we can have with these types of bimetallic welds arise from the metallurgical discontinuities across the weld zones, and that leads to strain localization and elemental diffusion, and it can give rise to certain unwanted microstructural features. So you can have things like a coarse grain microstructure, you can have a chromium depleted zone from diffusion across a fusion line. You can also have columnar grains due to the direction of heat flow, but also you can have columnar ferrite grains because of carbon depletion from the heat affected zone from carbon migration through to the fusion line. You can also have a fully austenitic zone, and that arises when you have 2 things happening at the same time. So if you have a high carbon content and you also have chromium depletion in the same area. You can also have thermal fatigue due to a mismatch in the thermal properties, and you can generate residual stresses in the joint, which can lead to crack initiation from high cycle fatigue or increasing the likelihood of stress corrosion cracking. You can also have general solidification cracking from solidification of the melt pool, as Richard discussed. And you can have sensitization of the stainless steel, which is essentially precipitation of chromium carbides around grain boundaries, making it more susceptible to intergranular corrosion. So all of that we prefer to avoid if possible. And I know Richard gave you a brief overview of rotary friction welding, inertia welding in particular. Here's a little video to illustrate. We have the spinning spindle on the left-hand side, the fixture on the right-hand side that applies an axial pressure. And again, to reiterate some of the advantages of this process over fusion welding, it's solid state, so you have no molten pool and therefore no solidification defects. And the fact it's fully automated is a big advantage due to the aging workforce and the skills gap in the nuclear sector. There's also no need for any buttering or filler material. And because of the localized intense heat and deformation at the weld interface, you get a very fine, nicely recrystallized microstructure that's similar to a forged joint and gives good mechanical properties similar to the bulk material. You have a narrow heat affected zone. There's also a lack of sensitization of the steel, and the process is very fast, so it's often less than a minute. and it's self-cleaning again, as Richard mentioned, because you can have oxide or debris at the weld interface, and that will be extruded as flash through the OD as we see there, and the ID, which can later be machined. And most rotary friction welding joints are very high integrity. The area of the bond is approximately 100% of the cross-sectional area, and it offers a high integrity joint every time. It's very repeatable. In terms of the AFRC's rotary friction welding capability, we have two machines that have a joint forging capacity ranging from 15 tons to 300 tons. We have MTI's tri-mode capability machines. By tri-mode, I mean that we're able to do direct drive friction welding, inertia friction welding, and hybrid friction welding, which is a combination of the two weld cycles. We're able to weld solid cylinders or tubular welds with outer diameters ranging from 35 millimeters to 250 millimeters, but essentially we're able to weld anything that's axisymmetric. Coming into a bit more detail about the different types of welding cycles. So essentially rotary friction welding was discovered by accident back in 1956 in the Soviet Union, and it was a machinist who accidentally welded his workpiece to his lathe. And since then, it's mainly been divided into two types of weld cycles. One mainly in the US being inertia friction welding with companies like MTI and Caterpillar, and one more based in Europe being direct drive with companies like Kuka and Thomson friction welding. And essentially, the difference between the two is how the energy is provided into the system. So in direct drive or continuous drive, your energy is provided constantly through the motor. So you take your spindle up to a predetermined speed and you maintain that speed for a period of time before applying a brake, all the while applying an axial force through your fixture part. And conversely, in inertia friction welding, you have your, it's a stored energy input into the cycle. So a flywheel's normally, a weighted flywheel's on the spindle. Again, you take the spindle up to the required speed, you disengage from the motor, and it runs under the kinetic energy of the flywheel until a speed of 0, all the while applying its friction pressure to create upset and form your joint. With both cycles, it's common practice that once you reach speed 0 and the part's cooling, you can apply a further forging force to consolidate the joint. And then you can also have hybrid friction welding, which is quite unique in our case, where you can have a combination of both welding cycles together. Here it's illustrating a portion of continuous drive friction welding followed by inertia friction welding. It means you can create more bespoke welding cycles. So in terms of post-weld analysis capabilities at the AFRC, we have an advanced metallurgical characterization suite of equipment, as well as a full residual stress measurement suite. And actually we have a dedicated materials characterization and residual stress team in-house. We also provide machining capability, so we can create our own weld rings. We can also extract samples for post-weld analysis. We also have micro and macro mechanical testing capability over a wide range of temperatures and strain rates. So temperatures being from just below room temperature up to 1,200 degrees C, and strain rates from maybe 10 to the -4 up to about 200 per second. We can also do post-weld measurements in terms of metrology. We have a CMM and a full metrology suite in-house. And we also do microstructural and materials modeling. Just a small example of that is we've done some recent modeling on a low alloy 8630 modified steel. And you can see that this is our simulation on the left-hand side here, matches quite well our experimental results in terms of flash formation and in terms of upset in this graph here. So focusing in on how RFW could be applied in nuclear, we'll look at a case study of the primary coolant nozzles in pressurized water reactors. And I've got two kind of example schematics from a paper by Wagner et al. In the International Nuclear Atlantic Conference from 2013. And in this paper, they basically found that stress corrosion cracks were forming in the stainless steel side and some of the nickel alloy buttering elements. And that residual stresses that were generated in the joint had a large effect on the behavior of these stress corrosion cracks. So as you can see, the amount of alloys that are present in between the low alloy Phoretic steel and the stainless steel, we decided just to try and join these both using solid state joining and see what kind of mechanical properties and microstructural effects we can have. Unfortunately, we couldn't find A508 steel, couldn't get our hands on it, so we had to go with A516 steel, which we feel still illustrates the general feasibility of the solid state joint. And these are the results of our welding trials. So very basic, we didn't have a lot of material. We had a baseline set of parameters where we did an inertia weld with a weld speed of 1,805 and a friction and forge pressure of 133 bar. We then, in inertia weld 2, decided to double our friction and forge pressure, and inertia weld 3, we decided to do a 50% decrease from the baseline, just to look at the effect on the mechanical properties and the type of microstructures that we could create. Again, just to highlight that these are by no means optimized at the moment. This is just a feasibility study. And these are the results that we found. So looking at the macro images, you can see that we have intact joining. There's no open discontinuity or macro cracks observed at the weld interface. There's no cracks at the weld notch at the base of the flash here. You can see that there's nice intermixing between the stainless and ferritic steel due to the mix of shear and compression deformation that they'd be experiencing. And you can see that, well, is a slight difference in the ferritic steel flash formation with increased friction and forge pressure. There's not that much difference in the stainless steel, as you would expect, due to its high temperature strength. And if we look more at the individual alloys microstructure, you can see in the base material we have a solution annealed condition. So we have really nice austenite grains with some delta ferrite and some nice annealing twins. There's not that much difference between the base material and the heat affected zone in terms of grain size. However, as soon as you get to the weld zone up here, you see that there's very fine recrystallized austenite grains and a larger amount of the delta ferrite material. As you go to the thermomechanically affected zone here, towards the weld zone on the right-hand side, you see there's more deformed and recrystallized grain. And on the left-hand side, it's more similar to the heat affected zone. But we don't see any evidence of any columnar grain growth or any of the microstructural defects that we would expect from the current manufacturing route. Moving on to the ferritic steel, you can see that there is very little difference in the microstructure of the base material, heat affected zone, and thermomechanically affected zone. I think that there's very little difference in the grain size. So the heat affected zone is about 12.48 micrometers and the thermomechanically affected zone 11.54. So not that much difference. The only difference is really in the weld zone, where we can see that we have very fine lower bainite grains that are a result of the temperatures that we experience within the weld zone and also the cooling rates within the weld zone. Looking at the hardness profile, we can see that there's a slightly higher peak in hardness in the weld zone due to the finer recrystallized grains, as we would expect, but there's not that much difference in the maximum hardness. So for all welds, the range of Vickers is from about 240 to 257 Vickers. And the overall trend shows a decrease in hardness with a decrease in the friction and forge pressure, as you would expect. Moving on to the tensile test results, we can see our little figure at the bottom shows that all tests failed at the same area, and it was actually within the base material of the A516 Phoretic Steel, which is what we would like. And we saw that if we look at the wee box here, this is our inertia weld 1, 2, and 3 results, and we see a higher yield stress and UTS as compared to both base materials at either side. Also, if we look at the graph on the right-hand side, we can see that in terms of friction and forge force, that the baseline weld exhibited the best strength. And there's also observed to be a decrease in ductility of the weld joint as compared to the base material. We also wanted to keep in mind some of the issues with diffusion and creation of different carbides that can be issues within the current manufacturing route. And we wanted to check there was nothing nefarious within our microstructures. And looking at this, you can actually see that the only thing we managed to find for 0.1 of our EDS point map and our map here was a manganese sulfide inclusions, which we think are really probably more to do with the parent material probably than the weld. And if we also look along the weld interface, we did an ADS line profile, and we see if chromium being green and nickel being blue, there's really not a lot of chromium migration across the boundary. That's over about 30 microns, and it's the same difference in the iron content. So it's nothing nefarious there, and there seems to be no evidence of sensitization of the stainless steel as well, which is good. So I'll just stop sharing my screen so that my colleague, Dr. Yanis, can now talk about the residual stress formation.
Okay, thank you, Laurie. 1 second to start setting. So the characterization work was resumed with a measurement of residual stresses. As Laurie has mentioned earlier in her slides, we offer in the FRC quite a range of different techniques depending on what we want to measure. We have X-ray diffraction, laboratory X-ray obviously for surface stresses. We have hole drilling equipment for surface and subsurface. We offer two different techniques, one with electronic speckle part and interferometry, which allows us to use the specimen assays, and one obviously with strain gauges. And then we have some more destructive techniques like the slitting method and the contour method, which are fully destructive, but they give us much more information, particularly for the bulk material. And we also have recently developed quite a lot of the technique around ultrasonic, which is not destructive and allows us to measure surface, subsurface, and bulk stresses, obviously average through the depth that we are applying the method, but it is still a very valuable piece of information. For this specific work, since we were going to do characterization, our go-to method was contour method. Anything that is going to be sectioned, we would like to take a look on that cut face and measure stresses and get a full cross-sectional map of the stresses acting at that face. Actually, I will try to touch briefly about the theory behind residual stress generation and evolution and the measurement techniques. However, we had another webinar in the past around that specific area, and it will be, I will highly recommend all of you to go and have a look on that one, because I will probably be going pretty fast through the next slides. With the residual stresses, we have quite a few different factors, quite a few different mechanisms which contribute. Obviously, we have the thermal aspect with the heat being generated. We have the deformation aspect, but also we have those metallurgical aspects. We are talking about steels and obviously the 516 steel. We have some transformation from the austenitic region to some penitic microstructures. This means that actually we have also transformation-induced stresses, both due to volumetric changes, but also transformation-induced plasticity. Obviously, all of these are well known and can be accommodated. Specific information regarding each one mechanism, probably we are lacking those ones. We need to do a bit more testing, but we also have quite a number of options with other softwares like JMAT Pro or some first principle calculation. What I would like to point out is that throughout the welding schedule, we will have that increase in the temperature, we will have the applied force, we will deform the material quite significantly, and then the material will cool down. So obviously we are measuring stresses at the very end of the process at an equilibrium condition, room temperature. We are not measuring those applied stresses. And all of these factors contribute to what we see. In these specific cases, and I think you have taken a note on the previous trials, the stainless steel is obviously stronger at the elevated temperature. That is why it deforms less than the 516 steel, and that actually means that we expect completely different stress profiles in these two materials. Talking about the theory and the mechanical model behind the generation and evolution of residual stresses, we have different strains being created from a number of different sources, from the elastic strain with the contribution of a young modulus. We have the plastic strains to do the formation. We don't have necessarily creep strains in this specific case. Probably if we were doing a heat treatment afterwards, we should take them into account. Thermal strains due to expansion. Obviously, I talked about the volumetric strain with the transformation induced from austenite to painitic in this specific case. It is not that easy to get martensitic formation with this specific alloy, at least not for the cooling rates that we are experiencing. Obviously, carbon diffusion between the stainless steel and the carbon steel can change things, but for this specific material, it is a bit, obviously it is much easier to have painitic microstructures, and you will see the reason later on. Something that sometimes people have neglected is to include also the transformation-induced plasticity, specific term just to accommodate the extra strain that comes from the phase transformation. But back to the residual stress measurements. As I said, contour method is one of our go-to methods. Basically, we are taking the part, we are sectioning it in an EDM simply because it offers the advantage of a stress-free cut. Then whatever stresses were locked inside that part, they are being released, and that is being experienced as a distortion in the cut phase. We measure that distortion with a CMM. However, we have other options as well with the GOM scan or with Alicona if we are looking for much smaller specimens. And what we will do is take those distorted phase, invert it, apply that as a displacement field in a finite element model, and back calculate residual stresses acting normal to that cut phase. This is a very well established technique. We have developed quite a few things ourselves around that area, and we are very, very happy with the results that we are getting. We actually measured the stresses on all the three samples following the characterization work. We have used standard material properties for 316. Young modulus is around 193 to 195. For 516, a standard value is 203. However, a minimum value can be down to 195. For this specific case, we selected to have a slightly difference between the young modulus to see what we will get at the interface. It's not that much, however, it's still quite significant. And you can see, for example, the cloud plot from the distorted phase for the first welding trial. And if the first, if the overall view is a little bit too busy, we can focus on the actual welding region, and you can see how the different curvature exists between the two different materials. And this curvature, that difference is what creates the residual stresses. Obviously, we scan both halves, we superimpose, we make sure that both halves are correct, and you can see how nicely both of these halves are matching each other. That means that we have done a very good measurement. And actually that was the fact for all three of our measurements. And as a summary slide of what we have measured, we can see the three different trials and the residual stresses being generated due to these trials. In the first one, stresses are being mostly concentrated on the stainless steel. There is some compressive layer between the two materials because of the mismatch of young modulus, and obviously because of the different information that these two materials are exhibiting. With higher forces, higher pressure, we exhibit bigger stresses, tensile stresses, obviously. And what can be said is that probably we can balance the residual stress generation with the microstructure and try to tailor for that specific need. It can become an issue if we machine out the flash, as we will be exposing those tensile stresses. And in this specific case, we are measuring hoop residual stresses, but we can carry out supplementary measurements with XRD and hole drilling on this cut face and get the full 3D stress tensor. We have not done that for this specific application, but that is in our mind for the continuation work. However, the differences were quite noticeable. We selected the pressure, we selected those welding trials to create distinct residual stress profiles, to create distinct deformation, and that was the whole purpose of the study. Not necessarily to manufacture something, but to try and get a bit more of experience working with this type of materials and see what we will be expecting. And obviously, we try to link everything with the modeling. Modeling of RFW, there is a number of different softwares that can definitely do it. Everything depends on the information that we have. In this specific case, we did practically not mechanical testing. So we used whatever data we could find from literature and from other sources. And I think we were getting close, but we were not that close. The flash formation for the 516, it is not what we have witnessed in the trials. The flash formation on the 316 is a bit more than what we have also seen. Temperatures, we are reaching about 1300, so there is a little bit of improvement. There's actually quite a lot of improvement that can go into these models. The thing is to try and follow, if you like, a good plan, a good practice. And that is what I will be talking about in the next slides. We need to follow the physics of RFW with that specific welding, if you like, schedule that we had. Everything depends on the friction to generate the heat. And for friction models, we can work with from first principles with Coulomb friction or with shear friction models, and use a slip stick model if we don't have any other information. Obviously, people who have been working in this area have developed their own empirical models, and these are quite useful, but typically they describe the average conditions. They don't necessarily describe the local conditions throughout the cross-section of the material. And that can be challenging, particularly when we are talking about scaling up and transferring what we have done with the smaller machines to the bigger machines or the actual manufacturing route. Some other very interesting models that are derived from physics-based calculations, but this we need to have obviously the information from the machine, which does not allow us to design the process for what we need. Heat generation is directly linked with the friction based on that velocity that the material exhibits at the interface. What we have done in the past is that we have tried to use the inverse heat transfer tools available from softwares like Deform and Forge, and back calculate what is the heat flux. if we have a temperature measurement at specific locations in the materials. And we found that at least based on our modeling, that we can get actually pretty close, and that will help us improve what we are doing with the heat generation. Quite a lot of discussion around material properties. We had some scattered data published and available online. We used those, but we did not get very good results. There are a number of different models. My personal preference is to try and use those models that correspond to the strain rate range that we are expecting. Johnson-Cook models typically are used for high-speed machining. I'm not so keen of. I kind of prefer those Hansen-Spitten models because they are mostly relevant to those kind of conditions. However, we can generate material properties from softwares like ChainMath Pro and implement it through tabulated data or use subroutines. In this specific work, we used information from the software SFTC deform and also from Transvalor Forge NXT. That was because we could not easily find those specific conditions. We lacked information about the material in the full temperature range, so it became a little bit challenging to model something. And obviously we had the discrepancies with the trials. Again, with microstructure, phase transformations, the kinetics can be predicted from ChainMath Pro. Pretty standard, I will say, work created the Tete curves for transformation from austenite to benite. For martensite, we have a different type of equations, but at the end of the day, these data are available, and we can see the reason of why we are getting those benitic microstructures simply because of the cooling rate and of the starting temperature, if you like, for benitic transformation. Everything goes into that equation that I have displayed earlier. We need to take into account thermal strain, volumetric transformation, induced plasticity. If we do that, we are getting closer. In this specific case, we didn't have good enough information for these two terms, so our predictions were a little bit off for the 516 steel. We're a bit closer, obviously, for the Austenitic because it is a much simpler system. However, we are not there yet. We need to improve, and standard values that we have seen from literature are not as useful. However, with the help of ChainMath Pro that we have actually access, we can build everything and improve upon that. And this is me with the modeling theory, if you like, and the direction of where we are going. I will pass it now to Lori to finish this presentation.
Thank you. So just to wrap up, rotary friction welding can offer significant advantages over traditional fusion welding techniques. And in the case study that we presented, we feel it highlights the potential benefits of adopting rotary friction welding in our next generation nuclear designs for the following reasons. It's automated, which means it can combat the aging workforce and the skills gap. There's no need for any filler material. There's no solidification defects, no stainless steel sensitization. There's a narrow heat-affected zone, no columnar grains. We can also reduce and potentially control the residual stresses by controlling the welding parameters, which is an interesting piece of work that we'd like to explore. And we also can improve the ultrasonic inspection because there's no attenuation of the beam because of columnar grain formation. And finally, what are our next steps? Well, we want to fully evaluate the bond strength. We also want to optimize the bond strength by looking at different interface geometries maybe, or different heat sinks. There's different ways we can optimize that. We want to do some fatigue testing. We also want to measure stresses in all the other directions, so do full 3D stress tensors, X-ray diffraction and hole drilling, complementary contour method measurements, and ultrasound-based techniques. And we'd like to benchmark and validate our finite element models. We also want to look into post-weld heat treatment. Is it needed? Is there a threshold residual stress that we can live with? Can we manipulate that through the weld parameters? Or could we even mitigate our residual stresses using vibratory stress relief, which is something we'd like to look at as well. So, next slide, please, Yanis. Thank you all for your attention. I'd just like to say a big thank you to the wider team that worked on this project as well. This wasn't just me and Johannes, there was a lot of really helpful people, and also just trying to get things done in the COVID pandemic was a bit of a nightmare. So big thanks to everybody who helped get some practical work done this year. And if there's any questions, thank you for listening.
Okay, well, thank you very much to Laurie, Johannes and Richard for some excellent presentation. I hope this has given you a good understanding of some of the work that the AFRC is doing in rotary friction welding, and possibly also an indication of what to expect from the group in the coming years. So, as Laurie said, now we have some questions. So I will just begin on that. So we've got a question. Rotary friction welding seems to be mainly used in the aerospace and energy sectors. Is there any interest to extend to other areas such as automotive sector? Who would like to take that on?
Yes, we'd love to extend into automotive. So rotary friction welding is quite unique in that it's suitable for high integrity components, but it's also suitable for kind of high volume, maybe low value products at the same time because of the fast weld cycle time. So there's different things that we could do. There have been suggestions of looking into crankshafts, generating them, because with our machines you have a way of actually defining where the cycle can come to an end with inertia friction welding, so you can target a specific angle. But then also looking at the future of automotive, so going down electric vehicle designs, what their structure will look like, and we have the FEMHub, Future of Electric Vehicles project within the AFRC as well, so we're working closely with them to look at how we can incorporate rotary friction welding into future electric vehicle manufacture.
Okay, thank you for that. I think another one, possibly for Johannes, is relating to the stresses measured, and it's saying you've measured hoop stresses. So what about other stress components, and which ones are more, or which one or ones is more critical?
As I mentioned earlier in the presentation, with the contour method, it is a destructive technique. We access those hoop residual stresses. What we can do is go and do X-ray diffraction and hole drilling on that cut face, extract those information, superimpose them with the contour method results, and reconstruct, if you like, the full 3D stress tensor. XRD can give us quite a good resolution, and I think it will be the recommended method, particularly taking into account that we have the two different materials, we have an interface, so we would like to measure, if you like, with much higher resolution. We need to obviously prepare those faces, but with a little bit of grinding, polishing, and obviously electropolishing, we can do this kind of work. Hoop residual stresses are not necessarily the most critical stress component. Probably axial stresses are also quite important. we can access the material at different, again, axial positions and do a contour cut measurement, and we can measure those stresses in that specific location, or we can try to recreate some kind of map, if you like, with the XRT working in the already cut face in the hoop direction. Newton diffraction is there. Access is a bit limited. Obviously, we need to go and in specialized facilities, but there is a number of other options that we will be doing in the future.
Okay, thank you, Johannes. I think this one's possibly for Laurie and or Richard. Do you see any barriers to RFW uptake in the nuclear sector? For example, any issues with existing standards?
I'll take that one if you like. I think
Sure.
yeah, probably the honest answer. Clearly, there's well-established codes that don't really cater for this kind of rotary friction modelling application. However, codes can be changed. There's numerous examples of codes being updated as new technology comes along. So I don't think it's probably not a barrier as such. It's just something that would need to be managed and would need to be addressed, and clearly proven that rotary friction welds are safe for the lifetime of a nuclear plant.
Also, just to build on that, the Royal Academy of Engineers did a publication in 2012 called Lessons Learned in Nuclear. It was a guide to best practice in welding, and it was a large consortium including key members of industry and TWI, and one of the recommendations was to include new welding practices that would increase the quality and integrity of joints. So it's actually been kind of recommended by the sector itself that we start looking at alternative joining routes if it would be of benefit.
Okay, thank you, Richard and Laurie. Just looking at time, I think we've got time for at least one more, maybe two. We'll see how it goes. So how do you deal with the different coefficients of friction with all these different materials?
Yes, one of the options, as I mentioned, is to start from a first principle calculations. So we have the slipstick model, for example, and depending on which material is the softer at that specific case, we can take into account the yield stress of the material and calculate an equivalent friction coefficient. Everything comes down to what will produce, obviously, the minimum friction, because that is the limiting factor in the terms of friction force, and that is being translated into the calculation. We have done that through proper subroutine, calculating for each contact point of contact temperatures, assessing the strain rate, assessing the velocity, the relative velocity, and then we can take into account the material properties at that specific condition.
Okay, thank you, Johannes. I think we can probably just squeeze one more question in, and so this one's more about the welding process. So how can you improve the level of flash formation in the stainless steel?
There are ways of trying it. So you can alter the interface geometry slightly. You could maybe try and make a bigger heat sink for the material, maybe changing the overall OD compared to the other. There's different ways we can optimize the actual welding parameters themselves. Various things that we can try and optimize that. Do you want to build on that, Johannes?
I think you have covered that. There is obviously Right now, what we also tried to do was to increase a little bit the flash formation on the stainless steel. That is one of the reasons why we increased the pressure. At the end of the day, it's all about the bonding, and the bonding doesn't only depend on the upset, but also depends on the plasticity. And as long as we have a good amount of plasticity happening at the interface, the bonding will be good. Trying to control, if you like, the flash, particularly not necessarily for those solid cylinders, because we can easily machine out of the flash at the outer diameter, but probably it will be more of a challenge for the inner diameter. We could possibly be looking about some different geometries and try to control it in that way.
Thanks very much, guys. I think that's probably, we're just looking at time there. We've run out of time. So just for me to once again thank Richard very much for making an introduction and a great contribution to this discussion, and also to Laurie and Ioannis. And I'd like to bring today's webinar to a close. If you've got any further questions, please get in touch. You can do that via either the NMIS or the AFRC websites. This webinar will be available on our YouTube channel in the next couple of days. And also, if I could ask you to please provide some feedback through the survey that will be emailed to you. And your feedback is really important to us, and that will be greatly appreciated. So, well, once again, thanks for participating. I hope you've enjoyed this webinar and that you'll perhaps attend some more of the upcoming webinars in the NMIS Insights series. Thank you very much and good afternoon.
Thanks, Stuart. And yes, just to reiterate, thanks again for joining us for today's NMIS Insights, and thanks again to our speakers from NMIS and also from Richard from Rolls-Royce. And as Stuart mentioned, if you don't mind filling in the survey, it is really appreciated and it does help us shape future webinars. And as Stuart says, we'll now just bring this webinar to a close. Thank you once again.